Hi everyone, my name is Nitin. I'm a software engineer at Meta, and today I'm going to be talking about holographic calling. This image is taken from Facebook Connect 2021. Here you can see that these two people are having a holographic calling. They feel like they are in the same space and they are able to have a shared activity. This experience is a lot more immersive and natural as compared to a 2D calling experience. It's done best in AR device, but it can also be experienced to a certain extent on devices such as mobile phones. This is the agenda for my talk. I'll start with setup and high-level components. After that, I'll talk about data compression and EBR. Then I'll talk about some challenges related to latency and bandwidth utilization. In the end, I will talk about summary. Let's look at what the ideal setup for this would look like. In the ideal setup, a user will be surrounded by cameras and sensors, which means they will have 360-degree coverage of their body. They will have access to a specialized hardware where they have no concern of compute and power, where this captured data can be processed, compressed, and they will have access to a dedicated fiber connection where this processed and compressed data can be sent without any latency, delay, or packet loss concerns. Similarly, on the receiver side, they will have access to specialized hardware again, where this data can be processed, decompressed, and then it can be rendered on the relevant device. However, a more practical setup is going to look something like this. A user will have maybe one or two cameras and sensors covering just part of the angles of their body, which means that the uncovered portions will need to be filled in by using computer vision and machine learning. Instead of having specialized hardware, they will likely have access to a portable device, which will have limited compute, which means that the algorithms and the heuristics that we run, they will need to be compute and power friendly. Next, instead of having a dedicated fiber connection, they will likely be connected to public internet via wireless, which means that they will run into all sorts of challenges such as bandwidth variation, jitter, packet loss, etc., which will require us to be smart about how much data we are sending and when. Let's take a look at the high-level functional components of this. On the sender side, first you have the capture setup. You are capturing the RGB and depth data per camera and per view. Next, using that, you will have to form some sort of 3D point cloud. This data might need some pre-processing, such as some cleanup or segmentation. After that, the data will need to be compressed so that it can be suitable to be sent over a public internet. For sending it over the network, we will use some sort of real-time transport library, which can control the end-to-end delays by doing real-time bandwidth estimation and packet loss recovery. After the data goes through the internet, on the receiver side, there will likely be a de-jitter buffer, which will take care of smoothing out any jitters introduced by the network or by the source. It will also help taking care of any packet losses introduced or any reordering of packets. Once we have the full in-order data assembled, the data will need to be decompressed. The decompressed data may go through some sort of 3D reconstruction, and it will need to be then rendered on the relevant display. So as you can see that these components are largely very similar to 2D calling. The main difference here is because of the 3D data, the 3D point cloud data being sent, and the 3D reconstruction and rendering that will need to be done. Let's take a look at the data we are sending and the requirements for compression. So the one is we need to send the RGB and depth data for each view. We will also have likely some metadata such as segmentation mask and view information, etc., depending on the platform, which will need to be sent. We will have audio or maybe even spatial audio, which will need to be sent. The data compression will need to support real-world networks, which have limited and variable bandwidth. The data and the metadata that is being sent here will need to be synchronized. RGB compression is a relatively well-studied problem. We have these class of video codecs that do a very good job at preserving visual quality. There's also a very good understanding of the artifacts and distortion introduced by these codecs. Depth data compression, however, is a relatively less mature problem, and I'm going to talk more about it in the next few slides. Let's start with an example. So we did a little experiment. We took some samples of RGB and depth using Connect, and we saved those images to disk. In the first pass, we kept them untouched and uncompressed, and we ran them through our 3D hologram generation pipeline. The resulting hologram from a specific viewpoint looks something like this. Please ignore the background here. This noise is as a result of some segmentation went bad, but largely you can see that the quality is decent except a couple of holes here and there. This served as the ground truth for our experiment. Now in the next pass, I kept the RGB files untouched, but I colorized the depth data and then I compressed it using H.264. After I decompressed it and I ran the RGB data and the depth data through our hologram pipeline, the result looked something like this. Here you can see that there are significantly more artifacts, black holes, noise around the edges, and floating points as compared to when we did not have compression. Here I used CRF2, which should be perceptually lossless visual quality for 2D videos, but it causes significant artifacts for colorized depth. This shows that depth is a lot more sensitive to quantization and compression as compared to RGB in texture. It also shows that the human visual systems models that form the basis for these codecs, these 2D video codecs, they are much better understood for texture than they are understood for depth. In this slide, you can see a survey of the available codec options for depth. Codecs meant for RGB, such as H.264, HEVC, VP9, and AV1, they wouldn't be good at preserving and reducing depth-related artifacts. They will all likely suffer from the same problem that I demonstrated for H.264. HEVC 3D extension is something that was proposed several years ago, but it has not seen much adoption, and there's no silicon support for it yet. It has some low-level depth map coding tools, but there is little understanding of how well they will perform at reducing depth-related artifacts in the final hologram. PCC, which stands for point cloud coding, was standardized by MPEG recently. It is meant for volumetric coding, but besides not having silicon support, has not been enough study in terms of power and compute requirements and how well it does in terms of preserving visual quality and keeping the compression rates high. I will come back to it in the next slides as well. RVL and TRVL are some depth-specific coding tools which can offer good compression, but they have very high per frame variability, which can make it not suitable for real-time applications. Then there is mesh compression. There are several algorithms available which can compress mesh, but they assume connectivity and they don't work very well on non-manifold geometry. So for example, if you want to compress hair or complex piece of clothing, then they are not going to do a good job. Now let's zoom in a bit into vPCC. So vPCC is a native dynamic point cloud codec, which is proposed by MPEG. In this codec, it does the encoding by projecting the point attributes, RGB and depth, onto the nearest bounding box planes. And then some patches are generated from those planes and they are put on a 2D stream. So this results in going from PCC volumetric data, it converts them to multiple 2D streams. Once you have the 2D streams, they can be compressed using any video-based codec such as HEVC or VVC. In our experiment, we took the reference implementation of vPCC and we took the reference data that was available with it. The data had around 700,000 vertices at around 4 Gbps uncompressed at 30 fps. When we used that data and compressed it using the reference encoder, we saw around 200x compression from it and 14 Mbps bitrate. Looking deeper, we saw that the geometry map, which contained the depth information, only had around 1.6 Mbps of that. The attribute map, which contained the color information, contained the majority of it at 11.2 Mbps. And the third stream, the occupancy map, which basically contains zeros and ones to indicate where in the geometry map and attribute map you have data, contained only 500 kbps. Let's take a look at the visual impact on visual quality of vPCC. On the left, you see the source here, and the right, you see the reconstructed image. And both of these take a screenshot from a specific angle. As you can see that the right image is slightly blurrier than the left side image. So there is some loss of detail and loss of quality here. Now zooming in a bit on the face, you can see now more details around the face. On the left side, you see the source, and on the right side, you see that there are loss of details around the critical areas and around the edges, which is expected as a result of any compression. So vPCC gave us compression rates of 200x, which are promising, but 14 Mbps is still pretty high for a real-time application on the public internet. The test data use 700K vertices, but we think that it can be brought down significantly by doing some smart decimation, by by using more vertices on more complex areas and using less vertices on less complex areas. We think that this can bring data rate significantly and bring it to more acceptable levels for real-time applications. But this is the tough part. Reference encoder for us took more than 30 seconds to encode per frame on a Windows i7 laptop. Now, this just goes on to show that there's a long way to go before this can be made practical to fit on a portable device and use it for any real-time application. Now, coming to the challenge of adaptive bitrate. For 2D video, ABR is a relatively simple problem. You start with a bandwidth estimate. You translate that to a video bitrate by typically subtracting the bitrate needed for audio. From there, you determine the encoder parameters such as resolution, FPS, and bitrate. This is a very well-studied space. You have models such as convex hull model to map bitrate to resolution. And you also have several visual quality metrics available, such as VMAP, SSIM, which can help you optimize your ABR algorithm. For 3D video, it is a significantly more complex problem. So you start with the bandwidth estimate here as well. But from there, you need to divide it into video and depth bitrate for each of the views. From there, you need to determine the encoder parameters for RGB and depth for each of the views. As you can imagine, this is a joint optimization problem. Here, you need to allocate the bandwidth across different streams. So you need to have an understanding of relative importance of those streams on the final hologram quality. There is no understanding or no model such as convex hull model available, which can allow you to map bitrate to depth for depth coding. And then last but not the least, there are no objective visual quality metrics available, which can allow you to build and tune this ABR. Coming to the transport part now, typically the transport library is based on UDP and it offers unreliable transport. It implements some critical features such as congestion avoidance, bandwidth estimation, loss recovery, etc., all designed to keep the end-to-end latency within the bounds of real-time applications. A very commonly used library here is WebRTC, which has good cross-platform support. Transport typically faces this trade-off triangle where out of bandwidth utilization, latency, and smoothness, you can only have two, and you cannot achieve all three. So if you try to utilize for, let's say, latency and smoothness, then you are going to have lower bandwidth utilization than you like. Now coming to the end-to-end latency challenge. It typically is comprised of three parts. One part is the sender side, where you have latency because of capture, processing, and compression. Then on the network transmission side, you have latency because of first, the minimum path delay, which is the property of the path. Then you have air interface delays and queuing delays introduced by the network. And then third, you have latency on the receiver side because of de-jitter buffer, which allows you to smooth the data. Retransmission buffers, which is there to recover from packet loss. And then if you do any processing or rendering, they might also cause significant latency. Now, the problem of keeping the end-to-end latency low is not unique to 3D video calling or holographic calling. It is also present for 2D calling. However, this problem is more challenging because of a few reasons. First, the processing of 3D data on the sender side and receiver side, it can incur non-trivial latency, which can put more pressure on the end-to-end latency. Second, the bit rates needed for 3D calling are much higher as compared to 2D calling. This means that you will have more air interface delays, you will run into more chances of congestion and queuing delays, and you will also need bigger de-jitter buffers and retransmission buffers. At first, it may seem like not much can be done, but there are a few areas where we can push the envelope to reduce the latency. First, we can work on reducing the bitrate overshoots. By doing better bandwidth estimation, congestion detection, and better encoder rate control, we can make sure that we are measuring the bandwidth very precisely and we are matching that bandwidth very precisely as well. This will help us reduce the size of buffers as well as reduce the size of any queuing delays. The second is we can reduce or completely remove the need on retransmissions for recovering from packet loss. So this means that we deploy advanced error correction mechanisms such as LTR, FEC, decoder error concealment, etc., which can allow you to recover from loss without having to retransmit the packet completely. There is plenty of literature on these techniques that I stated here, and there are more, but the adoption is slow. For example, WebRTC still uses Google congestion control, which I will come to in the next slide, and it relies on retransmissions to recover from packet loss. The second aspect of transport is better bandwidth utilization. In this graph, you can see a typical behavior of Google congestion control, which is the bandwidth estimation used by WebRTC. In this little experiment, we used a network simulator and we capped the network bandwidth at a certain level. The red line shows you the achieved average bandwidth during that interval, and the green label shows you the set bandwidth for that interval. And you can see that the achieved bandwidth is significantly lower as compared to the available bandwidth. So the bit rates needed for 2D calling can be much higher, as much as 2 to 3 times as of 2D calling bit rates, because of additional data being sent. Having a good codec can help here by reducing the bitrate while preserving the visual quality, but the bit rates are still going to scale per camera, and they are still going to be significantly higher as compared to the 2D calling. So this calls for doing our best job in terms of bandwidth utilization so that we are wasting as less bandwidth as possible and leaving it as less as possible on the table. Now, to summarize everything, I talked about 3D data and depth compression is a relatively unsolved problem, and this will need to be worked on to make this experience practical for real-world users. ABR, or adaptive bitrate for 3D data, needs to be studied and defined. We need metrics to objectively measure visual quality. Libraries such as WebRTC are not very optimized to handle higher bit rates for real-world networks. We need advancements in bandwidth estimation and error recovery, both to reduce the bitrate overshoot as well as to improve the bandwidth utilization. So that's it. I want to thank everyone for their time here. I also want to thank our team and our partner teams for all of their hard work on this, especially the remote presence team for giving me this opportunity to speak here. Here is my email if anyone wants to reach out to me for any questions or any ideas. Thank you.